This is our L-band phased array antenna for our senior capstone design project. The future of satellite communication belongs to the phased array antenna. The recent boom in satellite development has resulted in a dramatic rise in the number of satellites launched per year. Satellite communication requires a ground station to receive and transmit data. With the launches of the Starlink constellations by SpaceX, personal ground stations are going to become essential for satellite internet access. Our goal is to create an affordable and commercially available phased array ground station system which will allow us to steer our antennas towards a satellite to achieve a better signal-to-noise ratio than a single antenna system. Our team is as follows: Cameron Green, Marissa Navarro, Daniel Toth, Alexander Sid, and Stephen Dahl. To understand the basic concepts behind a phased array antenna, we will follow the path of the RF signal from the transmitter aboard the L-band satellite. The signal from the transmit antenna will travel through several mediums to our phased array ground station receiver. Due to the diversity in this space, each antenna in our antenna array receives the signal at a different phase. First, the signals will be received by the antennas and then pass through a low noise amplifier. After that, the signals will enter a bandpass filter to reject frequencies outside of our desired band. Finally, they will be input to our software-defined radios to be recorded and then phase shifted with our algorithm to achieve a better signal-to-noise ratio. In this animation, there are two signals simultaneously processed. Using one signal as a reference, you can see how adding a phase-shifted signal can either amplify or attenuate the reference signal. Our beamforming algorithm is designed to constructively shift and add signals arriving at an angle like a satellite's would. From this animation, you can see how transmitting a signal from multiple antennas at slightly different phases can steer a beam. The exact same concepts can be applied to receiving. Our antenna array uses 4 antennas in a 2x2 square matrix, each separated by a half wavelength. All of the antennas will receive the satellite at slightly different phases. By using our beamforming algorithm, we can align these phases to receive from the direction of the satellite, achieving better signal quality. Our first test was using our single antenna setup to receive an Inmarsat signal. Using a program called SDR Sharp with a plugin called SciTailC, we were able to receive and decode maritime safety net messages. The messages even indicate which part of the world they are sent for. Here's a message about Colombian ports closing due to COVID-19. Since we concluded that our RF front end was capable of receiving and decoding an Inmarsat signal, we could move forward with designing the array. One of the greatest challenges in creating a phased array system is synchronicity between the receivers. In order to accurately phase shift signals, the receivers must be sampling at the same time and not suffer from phase drifting. Our approach to this problem was the sharing of a clock. The clock on the SDR regulates the operation of all ICs on the board. Think of it as the heartbeat of the circuit board. If the boards share a clock signal, then there should be no phase drifting. The SDRs may not initialize at the same exact time, but an initial constant offset can be accounted for in software, while an indeterminate drifting offset cannot. We emailed an engineer at Newelec, the company that manufactures these SDRs, and he seemed to think that one SDR could possibly share its clock with 3 more boards. Our first solution was to use a master board that still contained a clock and wire that signal into a slave board that is missing its clock. Initial results proved very promising. We sent a sine wave into two SDRs that did not share a clock and two SDRs that did share a clock, and we found that drift was effectively eliminated. Another solution we decided to explore was the development of a programmable external clock board that could be used to supply the four receivers. The clock of the SDRs uses an unconventional 28.8 MHz signal. We found a programmable board produced by Adafruit that could support this frequency. The clock board can easily be programmed through an Arduino Nano, and even features a SMA output. It was at this point that we had a great idea. Why hardwire the SDRs together, which would create difficulties for troubleshooting and switching between clock interfaces in the future, when we could connect SMA cables to all of the clock inputs on the boards and just use splitters to distribute the signal. We were finally ready to test both interfaces and make a decision on what we would use moving forward. Both solutions allowed for the SDRs to operate, but the SDR master clock approach was unstable and would occasionally crash. So we decided to go with the Adafruit clock board instead. Now that we could successfully connect all four SDRs, we decided to conduct a test that was recommended by our L3 Harris advisor, Dean Telson, as well as our WinLab advisor, Richard Howard. Two stationary, synchronized SDR receivers would be monitored as a single transmitting antenna is moved around them. This test gave us insight to the radiation pattern of our antennas, as well as the accuracy of our beamforming algorithm. Marissa conducted the test at her home and sent us all the data. As a result of COVID-19 separating our group, we coordinated sharing enough antennas and SDRs so that we could all continue with individual research. From these initial tests, you can see that we achieved a 2.5 dB increase in signal-to-noise ratio with the two antenna array. With all of the necessary pieces coming together, we decided to build the complete phased array. It quickly became clear to us that carefully planning the array was essential to fitting all the components on one piece of plexiglass.
The final USB cable being put in for our initial prototype. Nothing happened.
Oh, and please don't ask us how long it takes 3 electrical engineers to screw in some legs. Once the array was assembled and looking awesome, we had to perform more testing to make sure everything was working together. Luckily, we didn't break anything during assembly, and everything ended up working with only 1 or 2 minor issues. Here are all 4 antennas receiving the Inmarsat signal. Before COVID-19, we planned to have our system integrated and assembled with time for troubleshooting and potential upgrades. Despite the delays we encountered, we have continued to develop simulations and testing conditions to aid in the performance of our system. Now that the full array was functioning, we are ready to test our complete project. We brought the array outside in an attempt to replicate the experiment performed by Marissa, except this time with all 4 antennas actively receiving. We used MATLAB to analyze the recordings we took before and after beamforming. With the frequency plot, you can see we achieved a higher average SNR with an increase of 3.5 dB. We successfully achieved better signal quality than a single antenna system as well as a 2 antenna system. We used a GNU radio block called multi-RTL to account for the initial phase offset of the SDRs. However, while looking at our recordings, we noticed that the SDRs would eventually suffer from phase drift. If we could modify the multi-RTL block to resynchronize whenever this happens, we believe that our system could perform even better. In an effort to continuously improve, we have already developed design modifications to our system. This would include the addition of a synchronization signal source in our RF circuit to implement a feedback loop for intermittent channel resynchronization, the optimization of our beamformer algorithm on the NVIDIA Jetson Nano by utilizing GPU-accelerated processing, and upgrading our RTL SDRs to Lime SDRs to increase usable bandwidth and sampling rate. The development of our phased array didn't come without its own challenges, some that we expected and some that we didn't. However, we learned how to effectively communicate as a team, tackle the difficulties of a true engineering project, and to expand our thinking and learning process beyond what we've needed before, using the resources that were available to us, not limited to the many experienced engineers in the RF field who have provided us guidance. We'd like to give a big thank you to the Rutgers ECE Department, Rutgers Wind Lab, the Space Technology Association of Rutgers, Cellgain, L3 Harris, and to everybody who supported us through this process. Professor Sarwate, Professor Godrich, Professor Caggiano, Professor Bajwa, Kevin Wine, Ivan Seskar, Dragoslav Stojadinovich, Richard Howard, David Coe, Alejandro Pironi, Vivian Suarez, David Pereira, Alex Almeida, Dean Telson, Dylan Houghton, as well as the GNU radio community, Rapids AI, the RTL SDR blog, and SpaceX and AGI SDK for video footage. Thank you for watching.